2, and then what do you realize? What do you realize? That you can end the read cycle. So end of read cycle by deasserting CS. Right? So the moment you assert deassert CS, which means CS has to go down. Right? So the moment CS it goes down, it is the end of the read cell. So then the data lines become in a high state, and then you can even remove what these values are after this. Right? So it doesn't matter whether it's high. My suggestion to you is please refer to Turing book for write operation. So I am not drawing it here. But I have tried to draw. So, so my question is, if you look at this read operation and you believe that is a timing diagram, right? So the cycle is from T0 to T2, right? And T0 to T1 is the access time. And this is how you draw a timing diagram. If you have any questions, I can take that. If anybody has any questions, I can take it. Convention. Any questions? Okay, so maybe there are no questions. So this was about statigrams. This finishes the discussion on statigrams. Now I can refer. I can talk about something which is called fresh page for that. I can talk dynamic RAM, or popularly called as DRAM. Okay, why do you want to have a DRAM? DRAM looks like, and then only T and so on. Yeah. So, okay. So if you look at a dynamic RAM cell called as a DRAM cell, right? So this is a DRAM cell. This is a DRAM cell. Only difference is in the cell. So this part changes, right? So if I contrast this with the SRAMs, I have one transistor against 6. If you see, this is the word line. This is the word line, and this is the bit line. Right? This is the bit line. See, this dot is used in diagrams to indicate that there is a junction here. Right? So there's a joint here. So for example, here there is no joint. So just because I cannot draw these two lines without, or some people will make it like a jump here. No, that is also possible. But I think that is not very neat. You can just let lines cross here and there. Wherever you want to indicate there is a junction, you should indicate by a dot. So this is the convention which we use all the time. right? So what do we see? We see one transistor against six. That is one difference that we see. The other difference that we see is there is only one bit line. This is opposed to the dual rails that we had for static RAMs. And okay, there is one more change here. The read operation, the read operation is destructive. What do I mean by that? That when you try to read something from this capacitor, it discharges the capacitor as well, which means you lose whatever is stored on the capacitor. How a read operation is performed is like this. So how do you do that? So to do that, so to read the cell, right, you do two things, right? You pre-charge the lines. That is one thing that you do, right? uh, you pre-charge the lines, then you sense the value. See, I would request Pulkit to mute himself, right? His uh, yeah, his microphone is creating disturbance. Yeah. So to read the cell, what you do is you first pre-charge the lines, then you sense the value, and then you do an additional step, which is called as the refresh step. The sensed value. Right? So this is how you read the cell. So you see, in that sense, this is different from static RAM. In static RAM, you were just pre-charging and sensing the value, right? So that is all that was happening. You were just pre-charging and then you were sensing, but here you have another step, which is a part of the read operation. Why this is required is because the read operation itself is destructive, which means that if you try to read a cell, you lose whatever is there on the cell. So it seems like refresh is a part of the read operation. That is one thing to appreciate. The other thing to appreciate is periodically you need to refresh cell, otherwise the charge on the capacitor decays through leakage resistance. So what are we saying? So what is this? This is something additional, right? So what are we saying? Suppose if you have a memory, right? If you build a 1-bit memory and you have something stored here on the capacitor, if you don't read or write for a long time, this charge will decay. If you read, certainly you will have to refresh. And I hope you understand that if you do the charge, right? So if you're reading and writing, it is fine. Otherwise, periodically you need to refresh cells. Otherwise, the charge on the capacitor decays. So this implies that you have a DRAM refresh overhead. Right, so you have what is called as a DRAM refresh overhead. Okay, so I can take an example to illustrate this point. Suppose I have a 4M cross 1 DRAM chip. And for the time being, you don't worry about it. Think of this as very similar to the SRAM. This is what is mean. So you do refresh on a row basis, right? And I will give you some values, right? So let us say cannot go beyond 4 milliseconds and each refresh takes 80 nanoseconds, right? So yeah, so very good, Pulkit. So how did Pulkit achieve get to that? So to implement this kind of a memory, you require so many cells. And the design guideline is you should try to make it as squarish as possible. So that is like 2K cross 2K. So 2K cross 2K would give you 4M. So that is how you get to 1048. Right? Very good. So I want to figure out the refresh overhead. Right? I want to figure out the refresh overhead. Right? Yeah. So can somebody guess how to calculate this? So I want to calculate that what is the overhead, right, in percentage, which would be required for refresh operations. You realize refresh operations are not read or write operations, right? They are not useful operations, but they are required to maintain the data, right? So, okay, so cell dimensions are 2K cross 2K. Yeah. Okay. So, can somebody guess? So, the refresh overhead would be 80. Sorry, right. So 2K, right? So this would be 2K into 80 nanoseconds. And if I want to express this as a fraction or a percentage, what should I do? If I want to express this as a fraction, so I should spend this much of time in refreshing. In how much time, right? So after how much time should I spend this? Every 4 milliseconds. Very good. So yeah, very good, very good, very good. So yeah, so 2K, so 2K is 2048. 2048 into 80 nanoseconds divided by 4 milliseconds, right? 4 milliseconds, right? So you should properly do that, right? And so how much do you get it as a percentage? You can try to figure it out, right? So how much percentage? Somebody can figure that out. That is a fraction. You multiply by 100, you will get it as so somebody can try calculating. Okay, what is the time? I think we are through with time. Yeah. So any questions here? I can take it. Otherwise, I'll stop. Any questions? I think that comes to around 4.1%. You just try. You can just check whether it comes to that or not. Right. So okay. So I think we'll stop. Can I stop? See here? Yeah, 4%. Very good. Very good. Yeah. Thank you, Shiva.